This is 3.5, and we're going to look at congruent and similar figures. So our learning goal for this lesson is that students will model and solve real-world phenomena using the properties of congruence and similarity. So I want you to write your learning goal in your notes, but let's talk about some of the things you have to be able to do to meet this learning goal. And these you don't have to write down. They're all on your learning goals and success criteria handout, which you have pasted at the beginning of the unit. So these are the 5 things we need to be able to do. We need to be able to determine if 2 figures are congruent, and we need to be able to determine if 2 figures are similar. Then we need to be able to find the lengths and sides of similar figures. We also need to be able to write either a congruency or a similarity statement, and we'll talk about what those are. And then we want to be able to use congruence and similarity to model real-world phenomena and make some different conclusions. So let's begin. When we talk about congruent figures, we know when we said we had congruent segments, they were the same lengths. Congruent angles were the same measures. But if we have actual figures, congruent figures have exactly the same size and exactly the same shape, right? So same size, same shape. So for example, one way to determine if 2 figures are congruent is to check to see if we can slide, flip, or turn one so that it fits exactly on top of another. So for example, if we have this circle here, we could just simply slide it right on top of the other circle and they match up exactly, right? Or another way we can slide is we don't have to necessarily go left, right, up, down. We could slide diagonally. So if I slide this one on top, they match up exactly. So we could slide it, or maybe we flip it. So if I took this one and watch this, we're going to flip it left, right. See how it lines up exactly. So we did a flip. Let's flip it back. All right, so we could flip it and it's going to line up exactly. Or we could take this guy and we could turn it and then it would lay directly on top as well. Okay, so slide, flip, or turn allows us to determine whether or not 2 figures are congruent. Congruent circles, it doesn't really matter. You can't really turn them and they still look the same. So one way to determine if circles are congruent is to check their radius. If they have congruent radii, then we say that the circles are congruent. So what that might mean in this particular picture is if we draw the radius in, maybe like this one here and this one here, we would know for a fact that those two, if we knew for a fact that these 2 radii were congruent, then we could say the circles were congruent. So how do I write that? Well, what we need is we need to have a label for the center point. So if the center of that circle were A, and the center of this circle was, I don't know, how about D? The way that we write that is we say that circle A is congruent to circle D. So let me show you the circle thing. See, it's a circle with a dot in the center. So we would say circle A, and then we use the symbol for congruent, circle D. And sometimes we actually tell what the radius is. We might say circle A with radius AX is congruent to circle D with radius DP or whatever. If we knew the endpoint of the radius, we could say that as well. Okay, so make sure you're filling in your left-hand column questions. How do you tell if circles are congruent? They have congruent radii. Well, what if we didn't have circles? What if we had an actual polygon? There's 2 specific things that we have to look for to tell if polygons are congruent. So 2 polygons are congruent if they have what we call congruent corresponding parts. Congruent corresponding parts. And the parts of a polygon are made up of by their sides and their angles. So for example, if we look in this diagram down below, we have 2 trapezoids. They appear to be isosceles, but I'm not really sure. But let's say we know that segment BC is congruent to segment HJ. Let's say we know CD is congruent to segment LH. Let's say we know AD is congruent to LK. There we go. And then let's say that these Last ones are congruent as well. And let's say it is isosceles, so BA and CD are congruent, LH and KJ are congruent. So what we see here is right now all we know is that corresponding sides are congruent. And that's really only half of the definition for these two polygons to be congruent. What else has to happen is the angles must be congruent as well. So we want to know for a fact that, for example, angle D corresponds to angle L. Angle A is congruent to angle K. We want to know angle C is congruent to angle H. We want to know angle B is congruent to angle J. So if we know all of those things, then we can write a congruency statement. Now remember, when we name a polygon, we name it using the vertices, and we have to name it in order. So the first one we might obviously call ABCD. So it's polygon or trapezoid ABCD. And then we can say it is congruent to this other polygon. Now we got to name it in order because we got to look at their corresponding parts, and that's what makes a congruency statement. So we see that angle A is congruent to angle L, but also angle K. But I want you to think about what comes after A. B comes after A, right? So we have to do it in the same order. So AB. So if I was going to start with K and then go to J, that would make sense because AB, segment AB, corresponds to segment KJ in the second trapezoid. And then we just go in order. So KJHL would be the second trapezoid. We'll talk more about these congruency and similarity statements in another example. Oh, let's go back here and let's talk about the question that should be here. How do you tell if polygons are congruent? Well, we're going to look to see if they have congruent sides and congruent angles. All right, now let's do another example. Let's list all of the congruent corresponding parts. Now what we have here is what is a congruency statement. And so that's really important because it tells me which parts have to be the same. And I'm going to copy it for a second here. Now one thing that I know, use this little arrow thing here, I hope this works, is that angle T corresponds to angle R. I know that angle J corresponds to angle C in the triangles, and I know that angle D corresponds to angle F. So that's the first thing that I can list because they go in the same order. That's the first thing I'm going to do to list the corresponding parts. So here's how we're going to do it. We're going to say angle, I'm going to save this in my toolbar here real quick. Angle T is congruent to angle R. We also know that angle J is congruent to angle C. We know that angle D is congruent to angle F. Oops, my angle symbol in there so we can name that correctly, angle F. All right, so those are some congruency statements for the angles. Those are all my congruent angles. Now let's talk about the congruent segments. Now, what I want you to look at is, here, let me get rid of these things for a second so I don't make my figure too complicated. What I want you to look at is the order again. So if I were going to have, for example, segment TJ, that would have to be congruent to segment RC in the second triangle because they go in the same order in the congruency statement. In a similar way, I could say that segment JD was congruent to segment CF. And I'm just showing you this little trick because it's a nice, easy way to figure out what's congruent without actually drawing the figure. But of course, we're going to do that as well because we should always start with a diagram. In fact, I should have already drawn a diagram, right? So segment TJ is congruent to segment RC. And then we can say segment JD is congruent to segment CF. But wait a minute, how many sides are there in a triangle? Well, we know that there's 3 sides in a triangle, so we should have one more congruency statement for the sides. So let's draw a couple of triangles here. Doesn't really matter. We're just going to draw them like this, and we really wanted them to be the same size, but they're pretty close. So I'm going to label the first one T, J, D. And then the second one is going to be labeled R, C, F. And notice how I labeled that in the same orientation that I labeled the first one, because angle T corresponds to angle R, angle J corresponds to angle C. And so far what we've mapped out is that side TJ here is congruent to side RC. We said that right here. And we also know that side JD, which I'm going to do in green, is congruent to side CF. We've said that here. Well, we got one more congruency statement that we need to make, and we can see that it's going to be side TJ is congruent to side RF. So let's go ahead and say that side TJ is congruent to side RF. And again, if you look to the congruency statement, that still makes sense. T is the first letter in the first one. Oops, that should be TD and RF. D is the last letter in the congruency statement, R is the first, and F is the last, so everything matches up and makes sense. All right, so we got all 3 sides and all 3 angles. Those are the congruent and corresponding parts. Okay, now let's talk about similar polygons. We say that 2 polygons are similar if they have the same shape, but not necessarily the same size. So what that means exactly is that their angles are still all going to be congruent, but now their sides aren't going to be congruent. However, their sides do have to be proportional. So when you're thinking proportion, what you need to be thinking about is equal ratios. That's what it means to be proportional, that you have 2 ratios that are equal to each other. So for example, if you look at this diagram here, you can see that these pentagons look like they have the same shape, but it looks like these sides in the second pentagon are much smaller than the first pentagon. And it turns out that, I don't know, maybe every single side is exactly half as big. Then all of the sides would be proportional. So we'll check out how to investigate if something is proportional in the next example. But our question that we're going to put over here is, how do we know if 2 polygons are similar? So let's look at an example here. Oh, and by the way, I should mention that the symbol for similar is a little squiggly. It looks like this. It's kind of like a little tilde that you see on your keyboard. If you know what a tilde is, it's that symbol next to the number 1. But it's like the piece that you put on congruent above the equal sign, but it's without the equals. All right, so if I look at this statement right here, the way I would read this would be that triangle FRY is similar to triangle DAY. The 2 triangles are similar. That means that all of the angles are congruent. Angle F is congruent to angle D, angle R is congruent to angle A, angle I is congruent to angle Y. But it means that their sides are proportional. So what we want to do is look for corresponding sides. So for example, FR corresponds to DA. I know that's true because look at my similarity statement. FR corresponds to DA. And I happen to know the lengths of both of those corresponding sides. So what we're going to do is set up a ratio of those sides, and that's going to be my similarity ratio. So 4 is the first side, 6 is the second side, write it as a ratio, and then reduce. So 4, 6 reduces to 2/3. So in this particular case, my similarity ratio is just 2/3. If I wanted to, then I could use that to find the lengths of some other sides. So for example, let's say this side was X and I wanted to know how big it was. Well, now I can use that ratio and the fact that I know the length of side FI to set up a proportion which I can then solve. So let's do that. I know that 4 is to 6 as, and what side matched up with the 4? What was the same? The 6 came from the same triangle, so 6 is to x. So notice that 4 comes from triangle FRY, and 6 is side FI comes from triangle FRY. So if we wanted to solve this, we would cross multiply. So then I would make the statement that 4x is equal to 6 times 6, or 4x is equal to 36. And then if I divided both sides by 4, I would get x is equal to 9. So we use that ratio to set up a proportion, and then we solve the proportion by cross multiplying. Okay, so let's do another example. Let's find the measure of angle R. Well, remember how we talked about corresponding parts being congruent to each other? So angle R must be congruent to angle A. Therefore, the measure of angle R has to be the same as the measure of angle A, and it has to equal 105 degrees. And it's that simple. If I wanted to, I could find the measure of angle D. Since F is 46, D would be 46. Could I also find the measure of I and Y? I could, because all my angles have to add up to 180. I could just add the two that I know and subtract from 180 to get the third. Now make sure in this example you're writing in the left-hand column exactly the questions from the example so that you could answer them later. All right, let's do one more example of setting up your proportion. We'll practice in class a lot more about how to solve these proportions, but I want you to be able to set them up correctly. So we know in this particular case that quadrilateral DEFG is similar to quadrilateral YZWX. And what I want to do is complete the similarity statements or the proportions that we have below using that similarity statement. So here's one way to do that. Let me get my pens here. I'm going to get my colors. I know that segment DE is congruent to segment YZ. So let's mark that. DE is congruent to YZ. And using our colors can be really helpful. EF is congruent to ZW. So ZW is here. And then FG is congruent to WX. So FG is here, WX is here, and then the last one, FG, is going to be similar to WX. Oh wait, we already did that one. Just kidding. The last one would be DG and YX. So DG and YX. Okay, so now let's use our colors to help us complete these proportions, these ratios. Here we have DE, and in my figure on the left, DE was marked with the black pen. And then in the figure on the right, we have segment YZ. And again, that is marked with the figure in the black pen. That's good. So black is to black as, let's look at the next one, EF was marked in the red pen. So which side was marked in the red pen over here? WZ. And so that's what's going to fit in right here, WZ. And let's even make it red so we know what's matching up. Awesome. There we go. So the length of side DE to the length of side YZ is equal to the length of side EF to the length of side WZ. All right, let's look at the next one. We have GF, so that's my green side over here, is to blank, as side FE is to side WE. Well, side FE again was the red side. WZ was the red side over here. So what we need to do is figure out what was the green side of this second figure. And so green is to green as red is to red. So here we would fill in WX. That's the green side. Let's even go ahead and make it green so we know what we were looking for in our notes. Now, If these had actual measures, we could fill in the measures and we could use the measures to solve for any of the missing sides that we were looking for. Okay, so go back and think about what's important for congruent figures, for similar figures, and setting up your proportions. Figure out if you have any questions and be ready to bring those to class on Wednesday. Um, and we will do some practice problems setting up and solving these proportions and using these congruent and similar figures and our congruency statements.